The unit circle, our old friend.
Our old friend that I absolutely remember nothing about.
Oh, good.
Yeah. Remember the like half pi, 3 over 2 pi? Yeah.
All right. So maybe we can remember that we were able to find any point around the circle, weren't we? Using the angle. Do you remember that? Using like sine ratio and cosine ratio. The whole point of the unit circle is that what's the radius length?
2 radius.
Radius is 1. So the radius is 1. This radius is 1. Yeah? That's why it's the unit circle, because a single unit, 1. And then you could find certain points around the unit circle if we knew what this angle was. How did we do that again? Can we remember how we did that?
Cosine. Or one of the,
Sine and cosine, yeah.
one of those rules, and then
Yeah.
cosine is the x-axis.
Yeah, well, it's not. Yeah, it wasn't really Pythagoras. It kind of was, but
It is root 2.
but we yeah. That you thought these lines were 1? No, the radius is 1.
One of them is root 2. Well, no, it depends on, you can't find out what the lengths are.
Well, if we have a right angle triangle and we know this side, we want to find this side. Let's not call it x. Let's call this one. We want to find this side. How would I find that?
You do cos.
What ratio is it? Yeah, you're on the right track. This is the adjacent side, and this is the hypotenuse. And cosine of the angle is the adjacent side over hypotenuse. Yeah, so the adjacent side is x, and the hypotenuse is 1. And anything divided by 1, of course, is just itself. Yes. So, in other words, this distance here from here to here is cosine, is the same as cosine theta. So that would be cosine theta. And then if you did the same process with sine theta, you'd find that this length on this side is sine theta, and then would give you this point, cosine theta, sine theta. Now maybe you're a bit sketchy on that. You should have done that in trigonometry.
Never taught it to us like that, but we know the point.
Okay. Yeah, you probably did.
Definitely remember hearing it like that. That was definitely the last.
This is probably not the first. Yeah, maybe it's the first time you listened, but no. Okay, and that also created this nice trigonometric identity, Pythagorean identity, that cosine squared theta plus sine squared theta is 1, which is also quite nice. But we're not looking at that, but that was just an aside, because Pythagoras' theorem, this side squared plus this side squared equals 1. Now, yesterday, for those who are here and not playing golf, we looked at the rotation by multiplication. And I had that spiral effect if there was any sort of scalar multiplication. So like 2i created some sort of spiral, which is kind of cool. So if we go back to our real and imaginary axes, so real and imaginary, and we created some sort of circles, and I was saying there's another way of representing a complex number. There's actually 4 different ways of we'll use 4 different ways of representing a complex number. The first way we've been dealing with so far is like the Cartesian way, or the complex plane way, which is so Cartesian. And yes, good point. This is an Argand diagram, but it's called Cartesian form. I know. Cartesian form is what we're dealing with. So that's like 2 plus 3i. That's Cartesian form, because it may represent on something similar to our Cartesian diagram.
You got the graph and the form?
2 plus 3i, yes. So it's about an imaginary axis intersecting with a real axis. Okay? And when we did some multiplications, some things happened to these complex numbers that just a multiplication without the I would bring the distance further away from 0, wouldn't it? And then if we had the I, it would start to rotate it around, if we remember that from yesterday. Now, we're going to combine, so this is 2 plus 3i. which is 2 units over and 3 units up, which creates this line as well. Now I created that line and that triangle because maybe we see the link between that and that. Now, the radius is no longer 1 on this, is it? In our unit circle, it's 1. That was the whole point of this unit circle, so I can end up dividing by 1. But this radius, we don't call it a radius anymore. Well, it is part of a circle if you were to draw one. We have a different name for this distance back to the center. It's a hypotenuse of a right angle triangle. It's actually called modulus. Modulus in, yeah. And it's got this symbol. So if z is 2 plus 3i, we get this z with a line either side. Now, we've seen that before. Absolute value. What is absolute value, the definition of it, when we may have come across it up till now? It's the whole number value, yes. So it's distance from 0. So that's an absolute value of a number. And for up until now, we've just been dealing with real numbers, which are only on this axis. So minus 6, it was pretty easy to calculate. Minus 6, the absolute value was just 6. But when we introduce the complex plane, it means that it's no longer just horizontal distance. It is going to be, it could be a diagonal distance, for want of a better word. It's not going to be just straight. This distance is the absolute value of this complex number. It's this distance from 0. So this thing is called a modulus. And it's absolute value. It's this distance. From origin or 0, whichever way you want to think of it. But it's distance from 0, from the center here. Okay? How do we create that? How would we find that distance? Let's say this particular one. How would we find? That'd be more towards its angle. Just the distance. How would we get this distance from here to here? You already said it earlier on. Pythagoras, yeah, because this is 2, this is 3. What's this distance in the triangle? It'd be. Its distance though is 3 units. Is this? Yeah. So the modulo of this would be 2 squared plus 3 squared square rooted. Pythagoras. So that's root 13. Now, if I knew this exact angle, I would be able to plot this complex number without knowing this. So if I just knew it was root 13 and the angle was, we're not going to work out the angle at the moment. Let's just say pi over, let's use pi over 4. Let's say pi over 4, angle of 45 degrees. You should be able to plot exactly where that is, yeah? You understand exactly where that complex number is?
On that one.
This is not the angle of this one. This would be a slightly different angle. But you could figure, so root 13, a modulus of root 13, an angle of pi over 4 is 45 degrees, and that distance is root 13, so the complex number would be right there. So we're going to use, but that's not the way we would write it. We have a different way of writing it. Yes.
So root 13 and angle 45, and so you just draw that to that point. Okay.
Yeah, and that's where that complex number would lie, and that's another way of writing. Instead of using this, with Cartesian form, we're going to use this form. Now, it's not written like this, but that's what it said. It's written like, or cos theta plus I sine theta, or being the modulus, that distance, and theta now theta will be the same for the same reason. It's the same angle here. It's this angle. It'll be same for cosine and sine to give this position. It's got a special name. It's called, if this is the modulus, this theta is called the argument. This theta is called the argument, and it shows the angle at which the complex number is. Now, I'm going to rub out this. Right. So, a couple of things about the argument. I'll just turn on the AC because I'm getting warm. A couple of things about the argument. Which axis is the argument from? Now, it's going to be the same. It's going to be the same as Same as when you did trigonometry. What axis did you start with the measuring from? Yeah, it's the horizontal axis. So in trigonometry, or up till now, we were dealing with just the x-axis. But of course, in complex numbers, that's not the x-axis.
Is it the real axis?
It's the real axis, yes. It's right. It's measured from the real axis. Now, in kind of opposite thinking to what you do in trigonometry, where you go from 0 around to 2 pi, in complex numbers, you go from 0 up to pi, and you go from 0 back to negative pi. For reasons that will become clear when we do a little bit later on in the unit, why we do that way. So it is from negative pi, the argument, up to pi. Now notice my symbols there. Why do I have one less than and the other one less than or equal to?
I have no idea.
Because there is like an ambiguous case here. What happens if it's right there? Which one do you take? Do you take positive pi or negative pi? Yeah, this tells us to take positive pi. If it's right on the real axis in this negative, like give me an example of a number that could be there.
Like -5 or something?
Yeah, just like -5 plus 0i. If you had the full complex number, that would have a
Argument.
the argument of pi. Yeah. Now we'll look at how we do this, how we get from there to here in a second. Yes.
I don't get argument.
You don't get argument. Argument is the angle. So every complex number sits at a certain angle from the real axis, the positive real axis. So one here is going to sit, and maybe you like to talk about degrees, it's going to be about 130 degrees. But we talk about in radians. So it'd be about 2 radians, wouldn't it? We'd be quite clear on our radians. Coming around to here, that's going to be from 0 up to how many radians? Which is what decimal? 3.14, yeah. Or pi, yeah. Yeah, well remembered. And this way is back to negative 3.14. Okay, so decimals or negative pi. So there is going to be our argument range. You're going to get something there. Now, do remember that it gets a little bit tricky because there's so many angles that have the same ratio, isn't it? Like cosine keeps hitting the same number. So we have to make sure we have our signs correct. But we know if we have the Cartesian form of the complex number, this form, what quadrant it lies in just by looking at it. Don't we?
Right, yeah.
Do we?
Yeah.
We should.
If they're both positive, then it should be in the
Yeah.
first quadrant.
Where is this one?
In the bottom left.
Exactly. You know straight away. You know straight away. So you should know what the angle should be. If you're talking bottom left, you know it's in this quadrant. You know the angle should be between, well, negative 3.14 and what's here? About? No, here. Well, that's negative pi over 2 or 90 degrees, or what would it be as a
1.7-ish.
yeah, 1.7. Yeah, half pi. Yeah. So you should know, you should be able to test your answer really quick. But you have to be able to get that link. Don't just rely on what your calculation gives you, because your calculation could have given you this one and the positive one sometimes. So just be aware. Now, I haven't shown really how to do that. I'm going to do an example now.
Since we're never going above like a full
The modulus symbol, so you'll see Z, this is the modulus symbol. It's the absolute value brackets is the modulus symbol. Okay, so now we're going to look at a straightforward, I'm going to convert. Does anyone know why I didn't try and convert this one?
No. Because it loops or something?
No, it'll just be in the first quadrant. What the modulus was fine to work out, it was root 13, but what's the angle going to be?
So it'll be 2 over root 13.
It's not one that's in this table. Remember our old friend? It's not one that's the 2 over 3 or minus 3 over. It's not in this. So I'm going to pick one that is in this table just to make the angle easy the first time, and then I'll get you guys to do one afterwards. Okay, so let's convert an easier one. Let's see, which I wrote one already. Z is equal to 1 plus root 3i. See a root 3 there, that's useful. Into, so what's this new form called? This new form, just started talking about the or and the cosine. Well, no, that's Cartesian. That's Cartesian. What's it called? Polar form. How did you know that? Ah, it's up there, yeah. Polar form, yeah. Into polar form. Some people call it mod argument form. Is this new form that we're creating. What's that form? Or cos theta plus I sine theta. So the modulus, this is the modulus, and the angle that it's at. Sometimes, some books shorten, yeah? Yeah, it's an R, yeah. It's R for the radius of the circle. Remember, so that was actually a radius of unit. It's kind of confusing, a lot of new stuff here. Some books use cis theta to shorten this down. Cos I sine theta. Because it's always the same theta here and here. It has to be. The complex number couldn't possibly have two angles, could it? In it? Like the real part has to be going at the same angle to meet here. That has to be the same angle for both. Cos theta and sine theta. Yeah. Cis. Yeah. It's a shortened form of this. That's just short. Means the same thing. I prefer this one because it actually tells you more and it makes more sense. Yeah, because you know that there's two locations, or sorry, not two locations, two coordinates. The one on the real axis and the one on the imaginary axis, which you might be able to see now, but you should see in about 2 minutes. So I'm going to convert this. Maybe I'll use a different color. Okay, yeah, okay. Let's find the modulus. Two. Now something I always like to do, and a lot of textbooks kind of don't do it, is I like to have a sketch. Why would I draw a sketch?
It helps you visualize it.
Yes, exactly. So it's going to be 1 over and root 3. So I know it's here. 1 over plus root 3i. So it's got this. So first thing I know is the angle is positive. The angle is between 0 and 90 degrees, or 0 and pi over 2. I know that about the angle. And the modulus I can work out by doing 1 squared root 3 squared. Now the modulus I'll write here. The modulus, or z with this symbol, you'll see that, is the real part squared plus the imaginary part squared, and we square root it. I'm not going to put it in brackets. I'll actually just go straight to square root. And we square root that answer. And that's Pythagoras' theorem. This distance squared plus distance squared, square rooted, I get this distance squared. Yes?
So the distance upwards is the distance of root 3?
Yes.
It's just not in scale?
It's in the same, yeah, but it's, yeah. Oh, are you saying my scale? Root 3 is slightly bigger than 1, so it should be slightly more than 1, yeah. It's not too bad.
Modulus is 2.
Oh, well, let's see. 1 squared is 1. Root 3 squared is 3. The square root of 3 is, right, okay. Is it plus or minus 2?
We don't know.
It should be plus 2 because we're on that side.
Distance can't be negative.
Oh, right, it's distance. It's not.
Distance can't be negative. We're talking about the absolute value of something. It has to be positive. It's its distance from 0. So it's 2 units from 0 diagonally. Okay? So if I was starting to fill in this bit, I know that the or is 2. Now I don't know what the angle is, but I have everything but the angle. I just need to find out this angle. How do I find out that angle? Yeah. You could also use tan if you want, because I know that's 2, yeah. I have everything I need. Yeah, which one is it? Well, the sine of this theta is the opposite over hypotenuse, which is root 3 over 2. The cosine of this angle is 1 over 2, which is a half. And the tan of this angle is root 3 over 1. Opposite.
Just do 2 over 1.
Whichever. 2 over 1 is not one of them. Which? So this takes us back to this table. How well we know our sine, cos, tan. I'll put it this way. Sine, cos, tan.
It's the secant.
Secant?
Yeah, 2. 2 is the secant.
Oh, why would you need that? Okay. All right. What's the angle? Come on. In radians, please.
It's 3 over 4 pi, right?
No, you don't. None of you know.
So you don't remember that?
Oh, you don't remember that? You did trigonometry last year.
And you did draw out the table. I can't imagine.
Okay.
Like 3 years ago, I used to draw on my class.
I've never been good at remembering it.
Is it pi over 3?
I know that way.
Okay. This is the way I do it.
I have it.
I do it the 1, 2, 3, 3, 2, 1.
Pi over 6. Wait, that's cos.
Pi over 3.
Pi over 6.
Starts with pi over 6, gets on to pi over 4, doesn't it?
Pi over 3, pi over 2.
And then pi over 3. Pi over 2 I'm not going to put in. I think I already have my answer here. What is? Which one is it?
No, it's pi over 3, because the cosine is only 2, not 3.
What am I looking at? Pi over 3. Pi over 3.
Yes, it's pi over 3. Okay, so the argument, or this angle, the angle is pi over 3, or the argument when we're talking about complex numbers is pi over 3. So what do I put here? Just pi over 3. And that is the polar form of this.
Incredibly complicated.
A little bit complicated, yeah. But this actually helps when we go to multiplying complex numbers, and we'll get to that. This form is better.
Could you theoretically do this with a Cartesian diagram too?
That is a Cartesian. That's a Cartesian diagram.
As in with like an x and y axis?
You can. You're asking, can you plot this on an Argand diagram?
Matt, can you put that on
An x-y axis? No.
no?
No. Well, you could put it just on the x-axis, but what's the y-axis then? The x-axis would have to have an imaginary axis with it, because the x-axis is real and it need imaginary. So wouldn't be on. You'd be talking about like a 4-dimensional diagram. That'd be quite difficult. Yeah. Okay. All right, we're going to try and do one just randomly. Who picked one? Ryan. We're going to convert one.
Wait, so all we have to do is find
The-
mod R.
Two stages. Find the modulus and the argument. The argument is the angle. And that's how we write it. That's the final answer. That's it converted into this form.
And this is all complex numbers.
Yeah.
So what's the
It's another way of writing the same complex number.
what is the actual polar form?
We will use it later on when we're multiplying, because it's actually easier to use this.
2 cosine pi over 3.
And you'll see that not today though, but it is a very useful form. This one is
Cosine theta.
clunky when you're multiplying. When you're multiplying by, like if you're cubing this or something, or to the power of 4, that's a mess, isn't it? You did some of them the other day and it took forever. But this one, if
So wait, if you told me that earlier, then I would have been able to do it faster.
yeah, but you see that's it. I'm making your life more difficult. It's my job. Yeah.
What's the result of the polar form?
This is the result of it. The result, how we use it, we're not going to do today, but I was just alluding to it. It's about multiplication and rotations.
Basically, we read it like that. Or we just
So we should be able to go backwards. We'll do one where we go from polar form back to Cartesian in a minute. It's a bit like converting between decimals and fractions. Which one do you use and when do you use it? Sometimes fractions are not very useful, and sometimes decimals are not very useful.
I don't think decimals are useful, unless you're answering.
irrational
and then-
numbers.
Yeah, that's one example. Yeah,
Well, you have a calculator.
yeah. When
The
you're
calculator would write it in a decimal form.
But you
when you're given when you're like when you're
It's an
getting
irrational number.
when you're given the percentage for a test. When you're getting the percentage for a test, it's better to get a decimal answer than a fraction answer.
When, really?
No, when you're given your result.
Oh,
And you got a score of 7/16. You don't know. You don't even know what's.
I mean, we can say it's a little bit below 50.
Yeah, you have an idea, but if I just gave you the percentage or the decimal, you know straight away what grade you got, wouldn't you?
I just used my calculator.
Yeah, I know, but that's it. Yeah, you convert.
0.63. 0.0633333.
Okay. Okay. All right. Ryan, I want you to give me any complex number. Now, don't give it in the first quadrant. Give it in one of these two quadrants if you can, just to make it a negative angle. Okay, minus 4. That's going to be over here, so you need something to bring it down. And minus again. Minus 4 minus 3i. Okay. Convert to...
Wait, I think that actually does.
No, it doesn't.
Is it 5? It's a 5.
I was thinking more of the angle, where it is. Yeah, we can get a decimal. We're probably going to get a decimal for the argument. Okay, let's have a little look at how we convert this. Steps.
Arg mod.
I like a sketch, straight away. Bang, where is it? Minus 4 minus 3i, somewhere down here. Okay. Okay. We're looking for this distance, which is its absolute value, or its modulus first. So the modulus of this is... No, I didn't even need the minuses, but 16 plus 9. So it's 5, yes. Okay, so the modulus is 5 away. That's great. What's the argument of this?
Okay, 4 over 5 into... Do we need a calculator for this? Or is that
Now, what angle are you trying to find?
Minus 3. You're trying to find the angle on the left.
This one?
Right now. Oh, wait.
Yeah, you are.
What's the argument based off?
It's all based on the real axis.
The positive real
And
axis.
we're going to the negative, so this one.
So it's going to be this way. This is the angle we need to find. Now we might use this one yet. We need this angle here. Does that make sense?
We're going to subtract 180 by the angle. we
Yes.
find.
Okay. Yes. So you can subtract if you need,
To find that angle, we would use minus 3.
and you know it's going to be negative.
It's probably opposite over adjacent. So
There's
10.
3
So
over 5.
Regardless of how you do it, do you need a calculator for this? Because we're trying to find the...
are any of the...
We do need a
None of these angles turn up on the table.
Well, yes.
I know that's the whole point. So you're going to need a calculator for that's what.
Okay.
This is one that's not in the table.
I think I need new batteries, Ryan. Thank you very much.
So you're going to need a breakout a calculator at some stage.
You do 10, 3 over 4.
So this is the triangle we have to use. We've no choice really. The 4 and 3 triangle with this is theta. What's sine theta in this case?
So
3 over 5? No, it's minus 3 over 5. Isn't it 4 over... No, it's kind of in this case. 3 over 5. Not exactly asking for the direction. Minus 3 over 2.
You could use minus 3 over 5, yeah? If you want. If you want, you can use 3 over 5. You just have to be sure of...
As long as you know the direction.
As long as you know, yeah, you know where it should be. So you can always rule out if it's wrong and find another one that has the same.
But sorry, sine negative 4.
No, it's
Sine is going to be opposite, so 3.
3 over 4.
Cosine, you could use minus 4 over 5 if you want. Tan, you could use 3 over 4. So let's just stick with sine and go with that. Sine is probably the best one because it's kind of set up already for you. But maybe. Okay, so anyone have a calculator there using it? So, how would I go from here into an angle anyway in general? What button do I use in my calculator?
inverse.
Inverse sine, yes. So sine minus 1, 3 over 5, and we'll do sine minus 1 minus 3 over 5.
Minus 36.8.
Okay, first mistake. That does not sound like between 0 and minus 3.14. Yeah. Okay, negative 0.64. Which one did you put in? This one?
Bottom one, yeah. Because it's negative.
Negative 0.64, yeah. Let's do, if I just have the positive numbers. Hopefully mine's in.
It's the same with positive.
Oh, sir. So
Uh,
another pet peeve I wanted to complain to you about.
Oh, complaint, yeah, my favorite.
So when we were in year 11, you would always refer to that as arcsine, and then we learned that that's not exactly how arcsine works in year 12. And I feel like you cheated.
Did I use, I think I just used
You
inverse.
definitely said arcsine, arc, cosine.
Did I?
You definitely said that in year 11.
That's possible, yeah. Yeah.
Sir, why do you have positive up there?
Just because there would be a relationship between this one.
Same.
Oh, yeah.
It's not, well, positive is 0.64.
That's what I'm saying, yeah. It doesn't matter, just like the direction as long as you know.
Yep. Are we happy with this as an answer?
It looks right.
Yeah.
Zero and negative.
Well, no, because then we have to find the other thingy in the middle.
No. Yeah.
Is this my final, is this what goes in here?
Put it in polar form, guys.
We have to do pi minus that number.
Yeah. Where is this angle? If I just drew this angle, that is here.
Yeah.
That is this angle. Yeah?
That's not where it is on the
You have to
What you found was this angle. So I got to minus it from 3 point. Yeah, okay.
Take it away from pi.
Okay.
So Burgundy, remember what we did over here. This, any angle from here to here is going to be from 0 back to minus 3.14. If I have only 0.67, that only gets this far. The first thing we realize is that this complex number is in this quadrant. So its angle cannot be that short.
Is that the same angle as that one? Is it, or is it just?
It's a reflection, if that makes sense. Yeah, so this angle, we found this angle.
Yeah, then find the other one.
The reference angle, if you will. Yeah.
The reference angle is a
Yeah.
reflection above the imaginary axis.
All right, so anyone care to tell me what the angle? 2.5. If you subtract from 3 points, so it's around 2.5.
roughly.
Positive or negative?
Negative.
So we used 3.4 and we 3.14 and we subtracted this and we ended up with minus 2.5.
Can we just like freely switch it between negative and positive? We're talking about subtracting the bottom number. Can we just like transform it magically from like negative to positive?
Oh, you tell me. What?
I don't know.
All right.
Because we know that it's in the negative, we can ignore the fact that it's negative until
And then just have a negative symbol on it?
No. What we found out is that this angle, let's not talk about the fact that we found it to be negative. This size of this angle is 0.64, yeah? And the size of this angle is 3.14. So if I subtract 0.64 from it, I get around 2.5, yeah? And if I go this direction, that's actually a directional negative 2.5. So the arithmetic we did without thinking about the signs, really, and then we figured out, all right, it's here, so but it's in backwards. So it's around negative 2.5. How do I write that then? So the modulus is 5, cos is negative 2.5 plus I sine negative 2.5. So we just pop in the angle there. That was a complicated one. It wasn't an easy one to find. Okay, we're going to do one now going the other way. I'm going to give you the polar form. Can we work back to the Cartesian form? And then you guys are going to start your homework. I'm going to pick a nicer one. I'm going to do root 2. So I'll write the question. Convert root 2 cos negative pi over 4 plus I sine negative pi over 4 to Cartesian form. Okay? If you want to have a go at this before I start, go for it.
So why do we have to find that long angle?
Because that's where it is. And the angle is always measured off this part. Yes, always measured off this line. So if it's in the second quadrant or the third quadrant, it's going to be, you're going to have to subtract some way off. Yeah, it's a bit like when you did the unit circle and it was an obtuse angle. And then, or if it was, you learned off this thing, remember this one? All sine is positive, tan is positive, cosine is positive. And you figured out whether it's positive or negative. But you could have logicked that out because cosine is directly related to the x-axis, sine is directly related to the y-axis, and then tan was one over the other. So you could have worked that out without learning that off by heart. We're kind of just working it out without learning anything off by heart, by drawing a sketch and knowing where it is. Because if it was the other angle, it would not be the same complex number. It would be a reflection of it in the imaginary axis, which would change the real value to the, so what you could have found was 4 minus 3i if you used the wrong angle. But we were looking at minus 4 minus 3i, which is over here, which would have a similar story, or a similar polar form, but same modulus, different argument. So now we're looking at this. How do I go about working backwards?
I start with the drawing.
Okay, you could start with a drawing. You probably might even need to draw. What quadrant is it in?
Third one.
So negative cosine.
This one. Probably the fourth one we got. Maybe. Or this one?
It would be in the second, wouldn't it? Because it's a negative cosine positive. Wait, was that a minus?
It's a minus pi over 4.
They're the same number.
Right.
It has to be the same, sorry. They can't, these two angles have to be the same. Hence why we can write it just as this, a short form with only one angle.
Wait, so how does it look when it's in like the second or fourth quadrant?
You can talk about degrees. You can talk, yeah, that's a short way of writing this. So this one could be written root 2 cis minus pi over 4. That's the same as that.
Pi over 4 is less than pi over 2. So is it in the fourth?
They're both negative pi over 4, right?
Yeah, it has to be, yeah.
Wait, so is it in the fourth quadrant?
It's here?
No, it would be in the fourth
Oh,
quadrant because it's less than pi over 2, right? Okay.
yeah. It's in this quadrant. It's got a distance, root 2, somewhere here. It's in this quadrant, and I know this angle is pi over 4. Yes? Which is? Okay.
You have the angle and you have the hypotenuse.
What is the cosine of pi over 4?
Wait, what is it? It's 45. 2 over 2?
I'm just going to rewrite this.
It's like 1 plus 1. That's the only way you get root 2.
2 over 2.
It's root 2 over 2 or 1 over root 2 if you prefer the other way. I know it says it here, so I will stick with that one, root 2 over 2.
Wait, sir, why isn't that over?
Okay. The angle is measured off the real axis. It starts here. Let's draw that again. The angle is measured from here. If it's positive, it goes this way. If it's negative, it goes this way. Okay? And then that covers everything. Yeah. Okay, so it hasn't reached pi over 2. Okay. Can we assign, we know what the angle is. Can we assign what the cos ratio of that angle would be? Root 2 over 2? Positive or negative? For cosine? In this quadrant? It would be positive. Root 2 over 2? And sine in this quadrant would be? Negative. Or you'd know that the I value would be negative because it's down here. And the real value should be positive because it's here. Yeah, so you can do it two ways. So you can minus root 2 over 2 like this if you like. I. Something like that. Does that make sense? You kind of know what signs they are anyway because you were able to draw it. You were able to place it in this quadrant. So the signs you should be able to get straight away. The root 2 over 2 you got from the table. And now we just apply in this root 2, multiply them both. And that will get us back to Cartesian form. Now what's root 2 over 2? What root 2? There's a lot of 2's. So root 2 times root 2 is 2, divided by 2 is 1. And the same over here is minus 1, or minus I. So that is that converted to Cartesian. Well done. Okay. Your homework starts with switching between polar and Cartesian. Now, I'll stop.